Now we want to turn our attention to scalable multiprocessors, multiprocessors that are larger than the 20 to 30 processors that we can put in a bus-based system. With a bus-based system, you need to start out with the infrastructure to support the maximum configuration, and that includes the bus, the cabinets, the power supplies, which need to be sized for the maximum configuration. If you add more components than that, the bus will saturate, and then the performance of everything will be diminished because transactions will take longer to go across the bus, so every memory transaction will slow down. A scalable system, on the other hand, is one in which resources can be added to the system without a hard limit. You can maybe make a system out of thousands of processors, and the cost will go up, but it will go up reasonably. It may go up proportional to the number of processors or a little bit more, but it won't be, let's say, number of processors squared. So scalability means there are no inherent design limits on how many resources you can add to the system. Bandwidth of the system needs to go up proportional to the number of processors. Latency should not. Latency should go up only very slowly as the number of processors increases, and cost too should increase approximately equal to the number of processors. A bus-based design doesn't satisfy this requirement because there are physical constraints. As the length of a bus increases, the propagation delay over the bus increases, and that forces a lengthening of the clock cycle because the clock cycle needs to be long enough to get a signal to the end of the bus. There's also an arbitration delay every time you try to put a transaction out on the bus, and if there are too many processors, you spend too much time arbitrating. There are protocol constraints. A Snoopy protocol requires that every cache see all the transactions that are made anywhere in the system, and that requires a bus which saturates quickly, as I said, about 20 or 30 processors. In a bus-based multiprocessor, the bus serves two purposes. First of all, it guarantees the transactions will be serialized. And that's what's needed for sequential consistency, that every global write will be seen in the same order everywhere in the system. But it also serves as a convenient broadcast mechanism to give information about the changes made in one cache to all of the other caches. If there's let's say, a read miss and another cache fetches data that our cache holds, our cache will have to change state. But it knows about the read miss because the read miss goes across the bus. Similarly, if we have a line in shared state and somebody else writes it, it will see that write miss and it will know that it needs to change its state in that line, usually to invalidate it if it's an invalidation protocol or update it if it's an update protocol. If we don't have a bus, we still have to provide cache coherence. We need to provide also the ability to access memory everywhere in the system. So we have to support a shared address space. Every processor needs to be able to access everywhere in the system. And we also need to be able to satisfy a cache miss, regardless of whether it misses to local memory or memory that's attached to some other node. And as you see the diagram down at the bottom of the page, you'll see that each node consists of a processor, a cache, a local memory, and a communication assist or network interface that's responsible for communicating with the rest of the system. And the rest of that system is available across the network. The network's made up of switches, and we talked very briefly at the beginning of the course about some of the topologies used in networks. A node in this processor consists of processors, caches, and memories, so it's called a PCM node. A coherent system must first of all provide a set of states, a state transition diagram, and actions. So we saw the state transition diagrams for the four bus-based protocols, and we're going to see state transition diagrams for the distributed multiprocessor cache coherence protocols that we consider. And we're going to see state transition diagrams for the distributed cache coherence protocols we'll consider in the next couple of lectures. It also needs to manage the coherence protocol by first of all determining when to invoke it, and secondly finding a source of information about the state of this block and other caches that may or may not require communicating with the other caches. That information will tell it where the other copies are, then it will go and communicate with those copies, which means that they can be invalidated or updated as the protocol requires. Determining when to invoke the coherence protocol is done the same way on all systems. Each cache knows what state each of its line is in. and then when a particular transaction occurs, like if you have a write to a cache line that's in state S, it needs to take some action depending upon the protocol. The difference between scalable cache coherence protocols are determined by the different ways they answer these questions A, B, and C, and we'll take a look at some of them in later videos today.